Have you ever stopped to think about what our digital worlds are actually made of? I mean, at the most basic level, it's usually just a single point of light, right? A pixel. But what if that point had depth? What if it had substance? What if, instead of painting a flat picture, you could build with intelligent, data-filled blocks? Well, that's where the Voxel Engine comes in. Today, we're going to look at how these simple 3D pixels are building some of the most complex and mind-blowing digital worlds you can imagine.
Okay, so let's get right into the fundamentals. For like decades, 3D graphics have been all about polygons. You can think of polygons as the skin of a digital object. It's this super efficient, hollow surface stretched over a wireframe. Great for making things look solid. But then you have voxels. And a voxel isn't just a point on the skin. It represents actual volume. It's a tiny cube of data in a massive 3D grid. It's really the difference between a photograph of a Lego brick and the actual Lego brick itself.
So here's the game plan for this explainer. We're going to start with the simple beauty of these digital blocks. Then, we're going to slam right into the massive hurdle they create, what I'm calling the billion pixel problem. After that, we'll see how a total revolution in hardware came to the rescue, how we literally had to learn to think like that hardware. And then, finally, we'll look at the incredible things all this hard work makes possible right now.
All right, let's start at the beginning. What really makes a voxel so much more than just a 3D pixel?
Well, the clue is right there in the name. Voxel is short for volume pixel. You know how a pixel on your monitor has a color value at an X and Y spot? A voxel has information at an X, Y, and Z coordinate. It's not on a flat plane. It occupies a real point in 3D space. And that's what gives the digital world true substance.
But here's where it gets really cool. Modern voxels are so much more than just on or off, occupied or empty. Now, every single voxel can be packed with rich data. It can know if it's part of a flat surface, or a sharp corner, or a gentle curve. It can even hold information about what it's made of. Is it metal, water, smoke? This ability to embed intelligence into every single point in space is what unlocks these incredibly realistic simulations and graphics.
Okay, so this sounds amazing, right? But there's always a but. All of that rich, beautiful, volumetric data comes at a price. A staggering cost, actually. The simple idea of a voxel grid leads directly to a data explosion.
Let's try to get a sense of the scale here. Your standard HD screen, 1920 by 1080, that's a little over 2 million pixels. Okay, that's a lot of dots for sure, but it's flat. It's just a 2D grid.
Now let's add that third dimension. Look at this. A tiny, tiny 64 by 64 by 64 voxel grid. I mean, this would be a speck in a larger scene. And it already contains over 250,000 individual data points. We're in a completely different ballpark now.
So what about a truly high-res, immersive world? We are talking billions of voxels. Billions. Each one a point in space that you need to track, calculate, and render. This is the billion pixel problem. How on earth do you even begin to process that much information in real time?
And hey, this isn't some new problem we just discovered. This quote shows that way back in 1987, researchers were already saying, whoa, this voxel data is so massive, it's a job for a supercomputer. The fundamental challenge has always been about scale.
For decades, this data problem kept real-time voxel worlds pretty much in the realm of science fiction. But then, a revolution happened. A revolution in hardware and a completely new way of thinking about computing that was tailor-made to solve this exact kind of problem.
Meet the GPU, the graphics processing unit. I love this analogy. Think of your main computer processor, the CPU, as a master chef. It's a genius, it's incredibly fast, and it can follow a very complex recipe step by step. A GPU, on the other hand, is an army of line cooks. You give all of them one simple task, like chop this onion, and thousands of them do it all at the exact same time. Now, for the billion pixel problem where you need to do a simple calculation on every single voxel, you don't need a master chef, you need an army. And the key that finally unlocked this army for general use was a platform called CUDA from NVIDIA. You can think of it as a special programming language, a translator that lets developers command the GPU's thousands of cores directly. Suddenly, the GPU wasn't just for graphics anymore. It was a supercomputer that you could have on your desk.
So how do you actually manage this army? Well, CUDA organizes the work into a strict hierarchy. You have the entire job to be done. That's called the grid. The grid is broken down into blocks of work, and each block is handled by small teams of 32 threads, called warps. Now here's the golden rule, the most important part. Everyone in that 32-person team has to do the exact same thing at the exact same time. Perfect lockstep. This is the source of the GPU's incredible speed, but it's also its biggest constraint.
So we've got the hardware. We've got this incredible parallel processing machine. But to really solve the billion-pixel problem, you can't just throw your old programming habits at it. It's not magic. You have to learn to think like a GPU. You have to structure your problem to fit its unique, massively parallel, lockstep way of working.
And that brings us to a super important concept, memory stride. Okay, picture your computer's memory as a giant bookshelf. If you read one book, then the one right next to it, and the one next to that, that's a stride of 1. The books are contiguous. But if you read one book, then skip 3 and read the 4th one, you have a stride of 4. Simple enough, right? So, why does this matter so much for a GPU?
Because of this. Just look at this chart. This data is from an old Cray 2 supercomputer, but the principle is more true today than it ever was. With a stride of 1, reading things right next to each other, performance is great. But the second you start jumping around that bookshelf, performance absolutely tanks. And for a modern GPU trying to feed thousands of hungry cores at once, this problem isn't just bad, it's catastrophic. The whole system just grinds to a halt.
So the holy grail, the thing every GPU programmer strives for, is called coalesced memory access. It's all about total efficiency. The idea is to make sure that instead of 32 different threads going to 32 different places on the bookshelf, you line everything up so that all 32 threads can grab one single continuous block of books in one go. It's one super fast trip to the library instead of 32 painfully slow ones.
All of this boils down to a set of golden rules, kind of a mantra for high-performance GPU programming. First, move data to the GPU and leave it there. Transfers are a killer. Second, use the little pockets of super-fast memory on the chip whenever you can. Third, and this is the big one, fight for that contiguous stride of 1 memory access. Fourth, don't let the threads in your warp start doing different things. And finally, and this one's a bit wild, memory can be so slow that it's often faster to just do a calculation all over again than it is to go find the answer on the bookshelf.
Okay, phew. That was a pretty deep dive, wasn't it? Memory strides, warps, coalescing. So let's come back up for air. What's the big payoff? Why do we go through all this incredibly complex optimization? What can we actually build with these hyper-powered voxel engines?
Well, one of the most mind-bending applications is something called image-based rendering. Get this. You set up rigs with, say, 16 or more synchronized cameras, and they capture a live event from every possible angle. Then a powerful system takes all of those video feeds and in real time builds a full 3D voxel model of the scene. This means you're not just watching a flat video anymore. You've captured reality itself as a digital object that you can move through and explore from any angle you want. It's like a real-life holographic replay.
And this kind of tech has huge implications. For military training, it means creating virtual scenarios that are so responsive and detailed they feel completely real. In the world of business, it's about remote meetings that capture all the subtle, nonverbal cues we lose on a standard video call. And for creators, it's a game changer. Truly immersive 3D modeling where you can reach out and sculpt digital objects with your bare hands, just like they were made of clay.
You know, when you step back, the story of the Voxel Engine is really a story about human ingenuity. We were faced with this problem of almost unimaginable scale, the billion-pixel problem, and we solved it by fundamentally changing how we think, by aligning our own logic with the architecture of our machines. It became a true partnership, which leaves us with a pretty fascinating question to think about. What happens next, now that our machines are learning to think for themselves?